Alright, welcome back. This will be the second part for our videos on polynomial functions. So in this video we want to talk about specifically the multiplicity and the turning points. So we're going to start with the multiplicity, and we're going to integrate the multiplicity with everything we talked about in the first part of this video. So I hope that you've watched the first part ahead of time. Okay, so the multiplicity is the number of times that a factor is repeated in our function f of x. So here's an example that we have a function, it's already factored for us. So each of these three parentheses here, because they're multiplied together to be the function, these are called factors. So we have a factor of 2x minus 3, we have a factor of x plus 2, and we have a factor of x minus 1. I like to use this table just to organize all the information because a lot of these things are connected. And so this is an easy way to kind of see it all at once in an organized way. To find the zeros, which maybe we've done before we got to the multiplicity step, we would set each part or each factor equal to 0. I think we can probably do this in our head. We can definitely do these pretty easily. This would be a 0 of -2. This would be a 0 of 1. This one's a two-stepper, so if I set it equal to 0, I would add the 3 over and then divide by 2. So 3 over 2 would be the 0, or if you wanted to make it a decimal, it would be 1.5. Okay, and then the multiplicity is going to come from how many times each of these factors is repeated in the function. So the 2x minus 3, it's raised to the third power, so it happens 3 times. The x plus 2 is raised to the fourth power, so it happens 4 times. The x minus 1 doesn't have an exponent, so it's implied to be to the first power, so it has a multiplicity of 1. Okay, so the reason why this is important to us, because we're trying to take the equation for the polynomial and use that to give us clues about what the graph or the curve will look like. The multiplicity affects how the graph interacts with the x-axis. So I have it written down here, and we'll maybe draw some pictures to give you a good idea what this means. A 0 with even multiplicity, the graph is just going to touch the x-axis at that point. So we'll come back to our table in just a second. If this is the x-axis, if I'm touching, it means I'm just going to say I'm coming from above this time, although it could be from either side. I'm going to hit the 0 on the x-axis and then bounce back. So this, we use the word touch to describe this, okay, or at least that's what I like to use. Another word that's good to use would be tangent. Tangent to the x-axis means that it touches the x-axis at just one point. So you may see the word tangent here and there. If not this semester, if you're going on to other classes, that'll come up very likely. Okay? And then if we have a 0 with odd multiplicity, then the graph is going to cross over the x-axis. So if this is the x-axis, this is our 0. If it crosses, it literally crosses from one side of the x-axis to the other. Okay, and so what determines whether it touches or crosses is the number that we have for the multiplicity. So we look at that number. So the exponent of 3, right, was the multiplicity here. 3 is an odd number, so that means when if I were to draw this graph, we're not actually going to draw this one, but we're going to draw a couple more in a second. This graph would cross the x-axis at 1.5. So we use this multiplicity number, even or odd. It's odd. That tells us that it crosses. And this is where it crosses at 1.5. Okay, for the factor x plus 2, it had a multiplicity of 4, which is an even number. So that means we're going to just touch the x-axis, and we're going to be touching it at -2. So that means we're going to come down or maybe come up from the bottom. We're not sure, but we're going to touch it at one point and bounce back. And then the last one here is a multiplicity of 1, which is also odd. So it's going to cross the x-axis, and it'll cross the x-axis at x equals 1. Okay, so this is called the multiplicity. We look at how many times a factor is repeated, and that's going to tell us whether the curve is going to touch or cross. So let's try it out. We're going to integrate this now with some of the things that we did in the last video. We're going to sort of do it all together. Okay, so we'll start with this function. We have x cubed plus 10x squared plus 25x. We want to find the zeros. So we're going to set really that's y. We're going to set f of x, which is y, equal to 0. This one would be good to solve by factoring. So I see that they all have an x in common. So I'm going to pull out a GCF of x. And then I can factor what I have left. So 5 times 5 gives me 25, and 5 plus 5 gives me 10. So I get 2 x plus 5s here. So if I set each part equal to 0, I'm going to get x equals 0 and x equals -5. We're going to kind of do that part in our head at the moment. Notice if I did set this parentheses, I'd get a -5, and if I set this parentheses to 0, I'd also get a -5. So we say that -5 is repeated as a 0. Okay, and that does affect some things as far as the graph and its shape. Then we can talk about the end behavior. What is the dominating term? Remember we said that was the term in the polynomial with the highest degree. If it's in descending order from highest exponent down to lowest, that'll be the first term. So in this case, that's true. So x cubed is our dominating term. So we could look back at that chart we looked at last time if you need to. Because the exponent is odd, the ends of this graph are going to go in opposite directions. And because there's an implied +1 out front, that can tell us what happens on the right-hand side. So the right-hand side is going to go to +infinity, and the left-hand side is going to go down to -infinity. All right, so now let's add in the multiplicity. If we look back at our factoring right here, I really just have two factors. I have x, and I have x plus 5. Okay, and so if I wanted to write this in a condensed way, let me just do that in case you want to see that. I could write this as x times x plus 5 squared. Okay, and you may come across it in both ways, either written twice as a factor or written as a square. These mean the same thing, okay, but it's two different ways to write it. We've already talked about the zeros, so if I set each part equal to 0, that's going to give me the zeros that I have found. Okay, how many times does x happen? 1 time. How many times does x plus 5 happen? 2 times. Okay, so if we look back at what we just were talking about, right? That's something we have to sort of remember for this chapter. So a 0 with odd multiplicity, like the x, is going to cross over the x-axis. But a 0 with even multiplicity, like the x plus 5, is just going to touch the x-axis and bounce back. All right, so we're going to be using all this information. We're going to integrate it together by making a sketch of the graph. So I use the word sketch because this is not a formal, we're going to plot a lot of points kind of graph. This is just an estimate of what we think the shape of the curve is going to look like. And we're going to put this information into our sketch in order. So we're going to start with the zeros. So I have zeros at 0 and -5. So I'm going to mark my zeros first. Then the end behavior starts at the outermost zeros. I only have 2 this time, so that's not really an issue. But from 0 on to the right is my end behavior. So it's going to go up from there. And from -5 on to the left is my end behavior. So it's going to go down from there. And then I need to incorporate the touching and crossing so I can finish the curve. I like to do this from left to right. It just makes it easier to kind of follow the same pattern and go in one direction. So at -5, go back up to my chart, I'm going to just touch the x-axis and bounce back. Okay, now I'm estimating how far down I go. So it's okay if I don't get that part exactly right, but I do come down some distance. I'm just estimating that. And then I need to go back up so that I can hit my second 0, and at 0 I cross over. And so I get a shape that looks sort of like this. Okay, now all of this information should jive together, should sort of dovetail into each other. So if I had touched here, you know, come down some distance and then come back up, because of my end behavior, I kind of knew I was going to need to cross through, right? So if all of that information doesn't match up, then you may want to go back and double check that you've done it correctly. The zeros should be the only place that we touch the x-axis, right? So it would not be appropriate to sort of add in some extra little squiggles here where we cross the x-axis in any other place. We are only going to cross the touch or cross, okay, the x-axis at the zeros. Those are the only places. All right, so let's try another one. This time we have f of x equals x to the 4th plus x cubed minus 12x squared. We can do something similar here. As far as the steps go, we're just going to follow the same process. First, we want to find the zeros. So we're going to put in the 0 for y. And I can solve by factoring here as well. So I see a GCF this time of x squared. And I'm going to have x squared plus x minus 12 left over. And I can go ahead and factor what I have left over. I need two numbers that multiply to be 12, and I think this time we're going to subtract them to be that 1x in the middle. So I think 4 and 3 are going to work really good. Because I want a positive 1 in the middle, I need a positive 4, and then minus or negative 3. So if I set each of these equal to 0, I'm going to get x equals 0. Negative 4, and positive 3. These are my zeros. Okay. Then we can talk about the end behavior. So what is our dominating term? Just like in the last example, we said it's the term with the highest degree. So this time that's x to the fourth. Okay, so because the exponent is even, that means that the ends of the graph are going to travel together like a parabola. This one has an implied positive 1 out front. So I can use that to help me decide the right-hand side is going to go in the positive direction, to positive infinity. And they're going to travel together. So both ends for this one should be going up. Okay, then I can look at the multiplicity. I have 3 factors this time. I always like to do one of these with you guys so that you can know what to expect. So really this is like 2 x's right here, x squared, right? It's x times x. So there's one factor of x. We're going to use the square as the multiplicity. Okay, and then I have x plus 4. And I have x minus 3. We just talked about the zeros, so we can fill those in if I set each factor equal to 0. Okay, and then my multiplicity numbers, because we have x squared, we're going to say that the x happens 2 times. X plus 4 just happens 1 time, and x minus 3 happens 1 time. So are we going to touch or cross? When it's even, we're going to touch. Remember, we're looking at the multiplicity number to decide that. When it's odd, we're going to cross. Okay, so then we can integrate that into a rough sketch of the graph. And like I said, we're going to start with this information that we just gathered in order. So we started with the zeros, so we're going to put the zeros on first. So I have zeros at 0, -4, and positive 3. Then we're going to add the end behavior. The end behavior starts at the outermost zeros. So from 3 on, we're going to go up. And from -4 to the left, we're also going to go up. And then we're going to incorporate the touching and crossing. Like I said, I like to go left to right. So on the left, I have -4. And at -4, I'm going to cross over. Again, we're estimating how low. We're not really sure how low we're going, so we're just estimating. Then I'm going to go back up towards 0. Notice at 0, I'm going to be touching the x-axis, not crossing over, so I touch 0, 0, and bounce back. And then on the right-hand side, same thing, I'm estimating. Maybe these are equal down here. I'm not really sure. It's okay, we don't have to know right now. We're going to look at the turning points later, which I think that's next. Okay, and then we're headed up toward 3. At 3, we're going to cross over, which is good because we need to meet up with the other end of our end behavior. And so we get a shape that looks sort of like this. Okay, there's lots of functions in the book that you can use to practice with. We'll definitely have some time in class to give you a chance to try this out. It's good to be able to take everything you know and integrate it together into a sketch. I think that part is very rewarding. Okay, so now we've talked about the multiplicity and we've sort of integrated all those parts. The last thing is to look at the turning points. We talked about what a turning point was at the very beginning of the last video, right? This is where the graph makes a turn, clearly. And we said it's going to count as a turning point if it changes from increasing to decreasing or vice versa, right? So if it was going from increasing to decreasing, then that would be a maximum. And so we're going to talk about how to locate that point. If it was going from decreasing to increasing, then this would be a minimum, sort of at the bottom of the valley. So there's usually a lot of math language around the definition for a maximum and a minimum. Basically, if we were to summarize that, it says that the maximum is going to have a y value that's higher than all the surrounding y values. So all these points around on the curve, around the maximum, they have y values that are lower because they're not at the top of the hill. Right? And likewise, for a minimum, it's going to have a y value that's lower than the surrounding points. Right? Okay. So there's two types of maximums and minimums. We can have a local max, which means it's a maximum over a section of the graph. So it's a high point, but it may not be the highest point on the whole graph. Okay, and then we have something called an absolute maximum, and that is the highest point on the whole graph. Sometimes we have an absolute maximum, and sometimes we don't. Depends on the end behavior. Okay, and likewise for the minimum. If we have a kind of a valley, we have a local minimum. A local minimum may not be the lowest point on the whole graph, but just in that area of the graph, it's a minimum. And then we have an absolute minimum, which would be the lowest point on the whole graph. So I usually like to use this picture to kind of describe the differences between these two. I'm going to draw, let's just say, I'm not going to draw the axis. Let's just say we have a curve that looks something like this. Can you pick out where the turning points would be for this curve? There are 3 turning points. There's one right here, one right here, and one right here. So let's label these just so you can get an idea of how to classify them. We'll go from left to right. Let's start with this one. What kind of turning point would this be? It's a minimum. Is it local or absolute? This would be a local minimum because it's a low point right here at the bottom of this valley, but there are points on the graph that are lower than that. So it's not the absolute minimum. It's just local. Okay, what about this one in the middle? It's a maximum. Is it local or absolute? This is a local maximum. It's a high point right at the top of this hill, but there are points at the ends of the graph in particular that are higher, that are going to go on to infinity. So it's not the highest point. In all honesty, there is no absolute maximum for this graph because the ends go off to infinity. So there isn't a highest point. Okay, what about the last one? It's a minimum. And if this is the lowest point on the whole graph, there are no sections of the graph below this point. So this is an absolute minimum. I hope that gives you an idea of how to determine local versus absolute. Okay, now we want to be able to come up with the coordinates for our turning points. We're going to use the graphing calculator to do that. So I went ahead and typed out the steps to find the turning point using the graphing calculator. If you are going on to calculus, you can do it by hand, okay, with the derivative, but we're not really there yet. So we're going to do this with the calculator. Okay, and I got 2 examples here. Now one of these examples, we don't really need the calculator for. Okay, so let's do these one at a time, but let's take this one first. What graph shape is this? This is a parabola. You can see the square. Okay, it opens up because I have just a positive 1 in the front there. So I'm not going to draw it on a grid. I'm just going to draw it sort of its shape. Okay, so we know it's going to be a parabola. How has this parabola been shifted? Should I write that underneath? Let's see. It's been shifted left by 2 and down by 3. Okay, and we definitely could have made a more specific graph with a grid and everything, but if I went from 0, 0, left by 2 and down by 3, where would this point end up? It would be at -2, -3. And what kind of turning point is this? Yeah, it's a minimum, and it's the lowest point on the whole entire graph. So this is an absolute minimum. Okay, so we did that one by hand because we know about parabolas and we know about all the shifting, and we just kind of put in everything we know. Now let's integrate that with the calculator. Let's see if I can try this first. Okay, so if I want to find the turning point, I first have to make the graph, which means I need to go to the y = screen, and I need to type in the function. So we'll go ahead and do the parabola even though we already know what the answer should be. So I'm going to type it in just as I see it. So x + 2 squared minus 3. And I can hit graph. Okay, and I see my parabola shape just like we talked about. Now, could I trace? The trace puts the cursor. Could I move my cursor over to where it is? Yes. Now sometimes it's a nice round number like it is here. I could even type in -2 and hit enter, and that would put me right there. All right. However, sometimes the vertex or the turning point is not a nice round number, and so we couldn't find it ourselves just by going and moving left and right. So this is why we have these steps outlined right here. So I want to do second trace, which is the calculate menu. Lots of interesting things here. We're going to be using the minimum and the maximum so that we can find the turning points today, but there are a lot of other cool things here. So we want, this one is a minimum, so I'm going to hit enter for minimum. And then I think you can see down here at the bottom, it's going to ask you 3 questions to give it a left bound, a right bound, and a guess. So you want to use the arrows to go somewhere on the left of the turning point. This is not an exact science, so you don't have to be in one particular spot on the left, just a safe distance so you know for sure you're to the left of the turning point. And then hit enter. And then it's going to ask you for a right bound, so we're going to arrow to the right. Again, anywhere on the right. Closer is better, but I would, only because it will take it less time to find it. But it's still going to be able to find it no matter what, as long as you're on the right. And I like to give it a safe distance so that I'm not right on top of the turning point. And hit enter. And then if you want, you can give it a guess, or you can be lazy and just hit enter. Okay, it's going to find it no matter what. It is a little bit more accurate if you try to make your guess a little bit more accurate. Okay, so there we go. There's our minimum at -2, -3. Okay, so this is the process we're going to use to find the turning points. I want to do one more example. If you have a different calculator, you may have to go and Google what the calculator steps are. They should be somewhat similar, and usually they are pretty similar, but you may need to go check that out. All right, so now let's try this example. Let me clear out that function. So we're going to do -2x cubed. Make sure you use the negative key, not the subtraction key. Plus 6x squared. Okay, so here's the graph we have for that. I think you can see we have 2 turning points. Let me just draw a general shape of the curve we have there. So we have a turning point here, and we have a turning point here. All right, so let's go from left to right and find the minimum first. So we'll do second trace minimum. We have to do the turning points one at a time. And we're going to do the same process. It asks us for a left bound, so we're going to move to the left. Probably you already have a pretty good idea of what this turning point is going to turn out to be, but I want to show you what could happen on your calculator when you do it. So then we're going to move to the right and give it a right bound and hit enter. And then we're going to give it a guess. Okay, so this one is at 0, 0. It is a minimum. Notice it is not the lowest point on the whole graph. We have an end over here that keeps going lower. So this is a local minimum. Okay, let me do that for you one more time because I wanted to show you something that could happen. So this time I'm going to give it a left bound. I'm doing the minimum over again. I'm sorry if that's annoying. Okay, this time I'm not going to give it a guess. I'm just going to hit enter. So it doesn't get right on 0, 0 this time. The accuracy doesn't really affect us because we're going to round it and we're going to end up rounding it to 0, 0. But I wanted to show you what this is. This is scientific notation. So this is 6.7. The E here means times 10 to the negative 7. I'll move this back in a second, but let's write that down. So this is like 6.7 times 10 to the negative 7. That means I need to move the decimal 7 places to the left. So that's 2, 3, 4, 5, 6 zeros in front of the 6, 7. Okay, so yeah, it's not 0, 0, but we're going to round it to 0, 0 because it's a really tiny decimal. Okay, and another maybe good point to make is, for whatever reason, I still haven't totally figured this out yet. Not every calculator gives you the exact same tiny little decimal. Probably just depends on where you put your boundaries. Those are affecting it a little bit as far as the process it's using. So, but irregardless, it's off by such a small, tiny amount, it's not going to affect our results, okay? Because we're going to round it to 0. Okay. All right, so that one is 0, 0. That's our local minimum. So let's do the maximum that we see. So we'll do second trace maximum. And same thing. Now we want to give it a left bound and a right bound for the maximum. So I'm going to be a little bit to the left of the maximum. Hit enter. And then I want to move my cursor somewhere on the right of the maximum. Hit enter. And as we've just seen, it is a tiny bit more accurate if you give it a guess. I'll leave that up to you. So we're going to round that to 2,8. Now I picked nice round numbers for this one. They're not always going to be exactly on the whole number like these are. Okay, so it's possible we might get 1.9 as an x value, and that's okay. This is the local max. All right, so I hope that gave you a good idea of what the multiplicity and the turning points look like. I hope you'll have a chance to practice integrating all of the 4 characteristics that we've talked about in the last 2 videos concerning polynomial functions. Thanks for watching.